The presentation this morning is entitled Validation of the Simulated Environment for Validating CFS Autonomy. After a brief introduction, we state the objectives and methodology followed by system usage review. After this, we detail the design of the experiments, system and dependent variables, and present the results. The previous presentation described the environment developed for CFS navigation validation. The state diagram was presented, the robot in its environment was described, as well as the arrangement of the ultrasound sensors needed for contact reflex in rear bumpers, as can be seen in Figure 1. This presentation showcases the findings obtained from the simulated environment developed for analyzing CFS navigation autonomy. Our objectives to identify dependent and independent variables for the simulated environment, to design experiments to determine whether the differences in system performance with or without an obstacle avoidance algorithm is statistically significant, and to present the findings. We identify dependent and independent variables, design experiments to determine whether the difference in system performance with or without an obstacle avoidance algorithm is statistically significant, and compare performance, compare the findings. Artificial General Intelligence, or AGI, recommends a functional structure of cognitive modules in which interdependent relationships between components are identified a priori. Cognitive theories may incorporate cognitive functionality as independently subsisting cognitive modules, where the modules are treated as atoms. Some other approaches involve incorporating agents. Braitenberg et al. Observes an openness in new conceptual frameworks for cognitive approaches to AI among researchers. Brown and Ellis introduced the cognitive function synthesis conceptual framework, and then recently we presented a paper describing the environment. This paper presents results to validate the simulated environment. Table 1 tabulates the system variables and dependent variables for these experiments. The system variables were determined to be 2 ultrasound sensor configurations, the 8 sensor and the 16 sensor, as well as use of the obstacle avoidance algorithm or lack thereof. The dependent variables were determined to be average wall contact per cycle, average cycle time, and average shock treatment. Shock treatment, as we mentioned earlier, to dislodge the robot should it get caught in a local minima, as Braitenberg can say. Algorithms tend to have a propensity to do. No? We envisaged 7 simulation runs for each of the combinations of system variables. The t-distribution with n-1 degree of freedom was used to establish the level of confidence we would need to be able to place in these results, and also the number of experiments that would be needed to establish that level of confidence. The dependent variables were calculated based on equations 1, 2, and 3. Figure 5 illustrates results presented in our earlier presentation as initial results. Results from the 7 simulations are displayed in tables 2 and 3. Table 2 tabulates the values of the dependent variables for each of the 7 simulation runs with both 8 sensor and 16 sensor ultrasound configuration when operated without an obstacle avoidance algorithm. The mean and sample standard deviation were also calculated and used to calculate the number of experiments required to be 80% confident that the mean values measured would be plus or minus 5% of the population mean. The simulations performed on the 8-center ultrasound configuration robot was sufficient to satisfy the above stipulated level of confidence. It was found, however, that simulation with the 16-sensor required a significantly greater number of experiments to establish that level of confidence. No? These results may possibly be explained by variations in the speed of the robot occasioned by the addition of the rare ultrasound sensors. Nevertheless, further experiments will be required to validate this proposition. Table 3 tabulates the values of the dependent variables for 7 simulation runs for both 8 sensor and 16 sensor ultrasound configuration with the Braitenberg algorithm, the results only garner the stipulated level of confidence for the result for the average cycle time for both level, you can say 8 cents and 16 cents. Figure 6, which gives the cumulative plots of tables 3 data, was very helpful in the interpretation of these results. Column 3 in the figure suggests that when the results of a small sample of experiments are very similar, there will be fewer experiments required to establish the stipulated level of confidence. However, the Braitenberg Obstacle Avoidance results for wall contact and shock treatment for the 16 sensor ultrasound configuration were very similar despite a few anomalous readings, especially in the earlier part of the simulation. These anomalies may very well be related to the starting position of the robot and may even be considered as outliers. Nevertheless, additional experiments would be required to validate this argument. Table 4 uses the student t-distribution to evaluate the performance by comparing the sample means of the 8 sensor and 16 sensor configuration for each of the dependent variables at 99% confidence. For the no obstacle avoidance, the null hypothesis was rejected in all cases, and this confirms that the difference between the means of the sample are significant and that the difference in performance is due to the ultrasound sensor configuration. For the case of the Braitenberg obstacle avoidance, the null hypothesis was rejected in all cases except for the average wall contact. While it is clear that the difference between the means of the samples for the average cycle time are significant and therefore due to the ultrasound sensor configuration, the difference between the samples for the average wall contact was determined not to be significant at all. This could be as a consequence of all anomalous readings occurring within the first cycle of the simulations. Shock treatment results was also found to be significantly different, but maybe due to anomalous incidents of shock treatment occurring within the first 5 cycles of simulation, not just the first. Again, further investigation is required to ascertain this. Table 5 compared performance of robot platform with and without obstacle avoidance algorithm. In all cases, the null hypothesis was rejected, indicating that the difference between the algorithms is significant. This implies that the environment can be used to establish significant difference in performance between algorithms, and as such, that the environment can be used for performance evaluation of other obstacle avoidant algorithms, including CFS. This validates the environment. In conclusion, contact collision simulation results show a difference in performance of the 16 sensor and 8 sensor ultrasound configuration was significant for all variables, while the Braitenberg obstacle avoidance results show that the difference in performance was significant for the average cycle time and average shock treatment. Comparing the performance between the Braitenberg obstacle avoidance and contact collision reflexes, where sensor configuration is held to be constant, the difference in performance is significant due to obstacle avoidance algorithm. These findings can only be predicated of this sample. Visiting the data to remove outliers may enable findings to be generalized to the population without the need of excess simulation runs. Thank you. If there are any questions.
Thank you very much, Jared. Well, I see the ultrasound sensors come back up again, so this will probably continue our conversation. So Jared, I have a question for you, or 2 questions here to start off with. Are you with us, Jared?
Yes, I'm here.
Great. So the first one is, did you use a sample size of 7 based on a calculated sample size formula? And did you have the opportunity to gather more data, or is this sample size justified from previous research?
Okay, so the idea was to take an initial sample and to determine what would be required to be able to establish let's say, to fulfill the requirements of the confidence levels that were specified, which was 80%. So this initial sample was to determine what numbers, what orders of magnitude you'd be considering. So then each experiment, each run is about 2 hours. because as I said, I have this thing running very slowly, 5-second sample, so it has to go very slowly for it to be the avoid latency and all of that. So then to run 225 experiments at 2 hours, and then so this was exploratory. The choice of 7 runs was exploratory to be able to determine exactly how things stood, as well as to determine what factors could be affecting those things for it to be able, I mean, that would cause the variation to be such that so many experiments would be required. So if that answers your question.
Okay, I see where you're going. It's time consuming for this basically. So you're governed by that constraint.
Big time, yes.
I hear you. It's very interesting, very interesting. So I have another question for you, Jared. This question is, do you have any consideration for further optimizing the configuration of the sensors to get the best behavior as part of the future work?
That could be done, even though, I mean, it's not my prime focus. My prime focus is to see how CFS would actually respond to this, you can say, to a repeatable environment. So therefore, with what I have, it is sufficient. Nevertheless, what you're saying is true. The thought has run through my mind as to how the 16 sensor configuration could have been adapted, such that you can say, if in fact it is, you can say, discovered that the arrangement of the 16 of the rare coefficients perhaps was the cause of the, you can say, the behavior of the performance of the 16 sensor configuration, then we can explore to see exactly how by changing those coefficients, it might be able to reduce those negative effects if that is the case. So that is possible. It was crossed my mind, but as I said, with 2 hours per experiment, that would probably be after I go for the kill, after I focus on demonstrating.
Yeah, I guess you would get past your initial sets of experiments and then look at optimization after.
Of the 16 sensor arrangement, yes, absolutely.
Right, of course. So I have one that's been along the lines of a question that's along the lines of future work. So would it be possible to implement a 3D obstacle avoidance system using the algorithm? For example, to detect and avoid examples and holes in the floor?
I have no doubt it's possible. I did not consider it for my purposes. I mean, I cannot see why it's not possible. I didn't contemplate it, but yeah, I imagine it's possible. I'm not one to answer that. I don't think.
Okay.
I wasn't focusing on that. I know that
So
the
I guess,
element
yes,
there. Yes.
Just go right ahead, Jared. Yes.
That Edelman and Krishma, when they were doing the experiments, they did also have, what I put it, sound sensors in different parts of the floor and so on and so forth. Yeah, so lots of possibilities are available. I was sticking to the you can say what was strictly necessary. But yes, it is possible. I imagine. I have not explored it.
Okay. So just to have a better appreciation for what you have done here, Jared, could you share with us?
Before you go on, I have one question.
Sure, Terence, go ahead.
Yeah. Well, I have to ask this because my question is, since you are using a behavior-based approach for your robot, how did you use the personality function to determine the behavior of the robot?
I've configured a behavior-based robot, which is very specific. It's a basically sub-symbolic robot which uses some memory functions. So a reactive robot with some memory function to be able to emulate higher functionality, more symbolic functionality. I did not use or take into consideration the Dennett stance of projecting personality to the robot. And so therefore the question of personality function, as Jung and all these guys would talk about, I did not explore. That was not the objective.
Okay, thank you.
Objective is to see, is to see how a series of associative memories can begin to take control of a robot and implement behaviors without actually specifically being told to. That's what CFS is all about.
Okay, thank you. Yeah.
So, Jared, let me, before I ask this question, I just wanted to say for the benefit of all, our next presenter is not online with us. So, Jared, just wanted to put it out to you if we could probably have discourse for 2 more minutes or so, if that's okay with you.
Go right ahead. Yeah.
All right, so one of the concerns that I had was what would be the biggest challenge that you face during this project? So you mind sharing with us what would have been the biggest challenge so far?
Wow, lots of challenges. So
I could imagine.
Yeah, so then I guess the first challenge was the framework. So the conceptual framework, cognitive function synthesis framework, to get a grapple, to get a handle on how this thing can work. I mean, don't get me wrong, to a large extent, it is our baby. It's our conceptualization, but at the same point in time, how do you measure this? No? So in the first paper referred to in 2017 was that first at trying to grapple with it, and so if we looked at those things which are easier to experiment with, which is basically reading its mind or looking at how it would process things without actually any external activity. And so therefore this work represents, well, let's say will represent, because I haven't shown any of the results for CFSs yet, will represent CFS acting outside of itself and so therefore impacting on its environment. So then, yeah, the first thing was conceptualizing it. So then after that, there was a question of getting the right environment in which how do you measure this thing? No? And that's when I came across, I can say the work of, Darwin's experiments, and therefore use that as a comparison. I could go on and on. I mean, problems galore, but to get an idea. So those are the major things. And after that, of course, was I was battling with a Lego robot trying to implement this, and I was advised by some very wise gentlemen. I guess it was Dr. Radix's group. They recommended that what I'm doing is best with a simulation. Yeah. And so then that set me on the path of looking at the simulation. It took me a while to get on the handle of the VRAP, and certainly I have to thank a good friend of mine, Minton Chen, who helped me through the nitty-gritty of it. Yeah, so then challenges all along, and certainly the Braitenberg getting stuck in the corner all the time to come to terms with all of that, and all of those things, different challenges we were able to overcome, thank God.
Right. It must have been very frustrating at times, I'm sure.
That's another statement. It has been, yeah.
Yes, I can appreciate that. I have one more question here. Are there any advantages of using the 8 sensor configuration over the 16 sensor configuration, since the cost may be a lot more?
Okay. Why did I come up with this? Why did we decide to go with 2 sensor configurations? No? Because, I mean, I don't know if you would have witnessed or seen the test between Tesla and Ford. But this is what I understand. I haven't actually seen it, and so I could be completely wrong. So,
Gerard, are you with us?
sorry. Yeah, I'm sorry about that.
Yeah.
I didn't want an unfair comparison, and so therefore I thought that the sluggish, you can say the fact that the 8 sensor was not moving away sufficiently from the wall, would have been, you can say, a bit unfair to compare the obstacle avoidance with something that is so sluggish. So then, for that reason, I said I need a more reactive reflex. So hence the 16 sensor. Yeah.
Okay.
But then again, that is just basic, you can say, intuition if you want. But certainly it is revealing because of the findings. So.
Now, just to probe on that, one last question for you. Are there any other sensor configurations that can be applied? So for instance, would you go up to potentially a 32 sensor configuration or something in between mindful, of course, that time is an issue. Would you consider that to show improved performance?
It could be done. There's always the risk of having ultrasound sensors too close to each other, so they start to interfere and interact, and that could cause some conflict. That could be done. It could be done. It's an interesting idea. Yeah.
Great, no problem. Well,
Thank
thank
you
you
very
very much. I appreciate the time that you have taken with us, and we have been able to explore your work in a lot more detail. Thank you for sharing, and we do appreciate the good work that you are presenting to us, and best wishes as you continue on this path.
Thank you so much. My